In this problem, we are given a triangle ABC with angle A equals to 45 degrees. E and F are moving points on AC and AB respectively, such that we have a point D outside of triangle ABC, where triangle DEF is going to be an isosceles right triangle with hypotenuse DF equals to 2. Find the maximum possible value of AD. So first of all, we realize that we have to use the information we are given. If we observe triangle ABC first, we notice that we are only given the measure of angle A as 45 degrees. And EF is going to be a rotating or fixed but moving side on AC and AB, meaning that the side length of EF is going to be staying the same, but then the placement of it will be changed depending on the positions of points E and F. So, since we have a fixed angle here and a fixed side, well, this reminds us of circles, because in circles, if you have a chord and then we have a point on the circle, we can use the inscribed angle theorem on it. This can help us find relationships. So first we can draw the circumscribed circle of triangle AEF. So we can just draw the circumscribed circle. And then we can call the center of this as O. Well, connect OE and OF. Notice that since we have angle EAF equals to 45 degrees, by the inscribed angle theorem, we have the central angle, in this case angle EOF, is going to be twice of that of the inscribed angle. So angle EOF is going to be twice of 45 degrees, which is going to be the right angle 90 degrees. So, also since, notice that OE and OF are both radius, so they're equal. This means that triangle EOF is an isosceles right triangle, meaning that this is going to be 45 degrees. And since triangle DEF is also an isosceles right triangle, angle EFD is going to be 45 degrees as well, meaning that angle OFD is going to be a right angle. This will come handy in the last part of the solution. And now observe the question. Find the maximum value of AD. Well, what triangle is AD involved in? If we connect sides AO and DO, well, realize that AD, to maximize it, since it's part of triangle AOD, by the triangle inequality, we know that AD will be less than AO plus DO. So that's the upper bound of it. How do we maximize AD then? Well, this is done when we have AO and D are collinear, meaning that they are on the same line. So in this case, when AOD are collinear, we'll have AD equals to AO plus DO. So, to use this, we want to find the length of AO and DO. So that is how we use the hypotenuse side lengths in this problem. Since DF equals to 2, we have EF equals to ED equals to 2 over root 2 by isosceles right triangle ratios. So EF will equal to root 2. Since EOF is also an isosceles right triangle, we have OF equals to EO equals to AO equals to root 2 over root 2, which is 1. So AO equals to 1. And now, how do you find the length of DO? Well, since we have angle OFD equals to 90 degrees, we have DO squared by the Pythagorean theorem equals to FO squared plus DF squared. So we have DO will equal to the square root of 1 squared plus 2 squared equals to root 5. So we have the max of AD will equal to 1 plus root 5. So that is how you solve this problem.